Today we're going to be taking a look at discovery and performance review of Fike Blue and thermal management. My name is Mark Kendall. I'm the General Manager of Fike FST here in Cwmbran in South Wales. And today I'm joined by Kevin Montgomery, our Manager of Fire Protection Product Management, and Tom Farrell, our Director and Principal Engineer of Test and Validation Engineering. Tom's going to take us through the bulk of this presentation. So without further ado, I'll hand you over to him.
Thank you very much, Mark. To everybody who's here, thank you very much for taking the time to attend. We got some cool things to talk about. With that said, let's just jump right into it. What we're going to talk today about is a brief history of and evolution of ESS fire protection, how we've gotten to the certain place of what we use, why we use it, what the narratives are behind their use. Real quick, talk about thermal runaway review, and specifically in the context of why historical fire protection doesn't really work in thermal runaway scenarios. We'll talk about some of our initial research and trials that we've done at Fike, trying to figure out how to control some of these battery fires. And then eventually we'll introduce Fike Blue and talk about some performance data and test data that we have gathered through the process of development and testing of Fike Blue. So first and foremost, let's talk about the early days of ESS fire protection. So we're dealing with lithium-ion batteries that are inside of an enclosure, packed really, really tightly. Energy density is king. Get as much in as you possibly can. When these catch on fire, it's not a metallic lithium fire like a traditional fire that you would have. And everyone kind of acknowledges that. They initially started thinking about things as, well, this is more or less an electrolyte fire. So electrolyte spills or vaporizes. And so start treating it kind of like a Class B flammables fire. Think of it as a pool fire where you have, diffusion flames, you've got your fuel volatilizing and mixing with oxygen and creating a fire. So initial protection schemes used a lot of typical Class B concentrations for inert gases or clean agents. And for a diffusion flame, that makes a lot of sense. But this really isn't kind of that same kind of hazard. The initial certification of agents with these were done on a really small scale. There's a lot of video out there of suppression tests being done of a single cell or a small stack of cells, just stacked together inside a small enclosure. The biggest problem with those kind of demonstration tests is that when you have one cell go into thermal runaway and create a fire, generally in the videos you can find on YouTube, they aren't electrically connected to each other. And also the events are relatively short-lived as far as the energy release from the stored electrical energy. And so what you're left with after that initial energy release is what looks like a traditional fire. It's the plastics that are remaining, the mylar catching fire. And so inert gases or clean agents can put that fire out pretty good. A lot of people were available to give free fire testing advice based off of what they understood, but doing a really, really large scale fire definitely was not part of the early days. It was, apply known techniques to a new or unknown type of hazard. And that has resulted, unfortunately, in some pretty major incidents. One of the biggest ones that everyone's pretty familiar with is Surprise, Arizona. That was a large ESS installation that was protected by a clean agent system designed in accordance with NFPA 2001. And so that, when you have clean agent inside of these containers, you have your typical ESS fire, and clean agent was pumped in, probably put out the fire inside of that enclosure, but it doesn't address the enormous amounts of heat that are generated. Unfortunately, a lot of the clean agents that are in use in the marketplace today, in the presence of either high pressure or high temperature, decompose into flammable gases, toxic or acidic gases as well. And in that particular installation, there was a large buildup of it. And unfortunately, when first responders first came to open that up, to assess the fire hazard. It then introduced oxygen into a very high heat, fuel-laden environment, causing an explosion. Another one is the Warwick, New York installation. That was an aerosol-based system. And the aerosols, again, will put out diffuse flames, but they don't address the high heat. They don't have the heat capacity necessary to carry that heat away to stop any kind of thermal runaway reaction or even control the heat generated by it. But they probably put out those initial diffusion flames. So in both of these installations, as well as numerous others that have occurred, did the system put out a fire? Yeah, likely, yeah, it probably did. But was that the actual problem that we were dealing with, and was that the actual hazard? As you know, because you're here, the real problem in these scenarios is propagating thermal runaway. And that is, an extremely dangerous, somewhat predictable, but it can be unpredictable depending on electrical configurations. But it is a process where one cell propagates to another cell, until you have enough heat in a module that it propagates to another module. And then that can involve an entire pack to pack and then move throughout an entire rack. A lot of causes for these. It can be a single cell that begins to fail because it's damaged or because of a manufacturing flaw that creates an internal short, and that causes it to go into thermal runaway. That can cause an electrical short to ones that are electrically connected in parallel, as well as thermal conductivity failures in adjacent cells. And then that just keeps causing a chain reaction. Obviously, the heat generated by these, either from flame or just the exhaust gases coming off of them, the heat from that can cause additional cells to go into thermal runaway as well. And all of this results in severe levels of toxic off-gassing. It causes explosion and obviously fire hazards. And what is also concerning is sustained thermal load. So if this is near another structure or inside of another structure, it can then cause the fire to propagate outside of the ESS or battery backup if it's a smaller scale system. Now the fires, just the fire, the mylar, plastic parts, parts of the casings, those fires absolutely can be suppressed with, chemical agents, inert gases, aerosols, various types of water applications. Those can handle those fires without too much of a problem. But again, the real threat persists even in those situations, even if you're addressing the burning of the hydrocarbons that are being generated. And so it says what the real problem is that it's a heat management and a thermal problem. And again, if you put out the flames, even if you put all those out, the problem is once your agent is no longer there, you can have reignition of those flames even after the suppression system has fired, after gases have dispersed. And that reignition then becomes a problem when you can have fires that burn for days on end. And one of the big issues right now is that on a lot of protective system installations, the fire protection professional who is responsible for the system will say, yeah, we extinguished the fire. Our system is a fire extinguishing system. The added thermal threat and thermal event that comes along with thermal runaway, that's not my problem. So you have these end users who have these systems that they think are protected. And in reality, the real threat of thermal runaway in an ESS isn't handled by anyone. And there's kind of a liability loophole that's just kind of hanging out there. So at Fike, we have taken a lot of time to think about this problem, and we've got various test facilities that we use for this. And we've used that to conduct research on lithium-ion battery fires. And we're going to talk about some of those facilities, and we're going to talk about a specific case study that eventually led to the innovation of Blue. At our labs, we typically focus on the unit or installation level testing. So it'll either be one large module or collection of cells, or a rack that is populated with those modules. Within our facilities, we charge and we monitor them during the test. All of our tests, we place our modules into thermal runaway using heating. You can do this with a nail puncture. But a nail puncture actually ends up releasing less energy than heating of the cell. Um, and that's partially due to during a puncture, you start thermal runaway in a very small spot, whereas with heating, you have the entire, in this example, the entire pouch getting very close to the point of thermal runaway failure. And then when one spot eventually does go into thermal runaway, the whole battery goes immediately, releases the maximum amount of energy. So we're always very conservative in our tests. And you can see our labs in some of these issues here, or the pictures here. We're monitoring temperatures in various locations inside of the pack, outside of the pack, heat flux on target surfaces around, both in accordance with guidance in UL 9540A and also in some other places that we know to be strategically important for a client, whether that is sensitive equipment nearby, battery to battery, spacing to help them optimize their spacing as well. Basically, we're doing a UL 9540A test without gas measurement. We do engage in direct calorimetry, and the reason we do that instead of using a traditional or a different type of oxygen limited cone calorimetry is that these batteries and the energy they can release can generate a substantial amount of heat that is not captured in oxygen consumption calorimetry because the heat is not released as a function of consuming oxygen. So you end up with a more accurate and higher level heat measurement when you do that. We can do gas measurement. Typically on these initial tests, we don't. And we can do a lot of different battery types using one of our battery hazard analysis test programs. So one of our early trials was the battery that you see here. It has 36 NMC pouch cells all in one case, and it's in the 3P12S configuration. So it runs at about 48 volts. The container that it sits in, seen here with the case off, is designed for containment and to keep the flame inside when flame exists. All these tests were done at a 100% state of charge. And as I said before, heating of these cells was done, thermal runaway was initiated by heating the cells internally at a low rate, so right around 4 degrees Celsius per minute. And 9548 gives you a range of 4 to 7. We find the slower you go, usually the more energetic things are when they fail because it gives more time for heat to disperse into the rest of the pack as well and put everything on a little bit more of a hair trigger. So this is the battery pack that we started with, and was working with a customer who both wanted to understand the thermal runaway threat in their battery, as well as try to find a solution for dealing with that particular hazard. And while we were doing this, we were measuring a lot of things, but the big ones that we were measuring were the core temperature, very close to where the heater was. The internal vapor temperature, very close to where the gas vents from this particular enclosure. The external case temperature, so you get a feeling for how hot it might be for other things that might touch it, or when we could approach and touch it from a safety standpoint. And then measuring heat flux in kilowatts per square meter and temperature at a nearby target device. So we know, what's the likelihood of propagating thermal runaway from module to module. And we measured both above and to the side. And again, wherever our client needs to have that information for their specific application. And our original trials were saying, okay, well, we'll do it kind of the way everyone else has done it, with gaseous Novec 1230. Did nothing, even at the highest allowable, the no observable adverse effects limits, which is close to 15%. We also tried it with liquid injection directly into the module, which actually did not do anything. You can see the results of some of those trials, and the battery in the very back, you can see some very high levels of heat staining associated with that Novec 1230 test. It all evaporated, went away. We tried doing this with a sludgy and thermal inhibitor, which I can't say the brand name here. And that actually didn't do anything either. It did help heat stay close to the batteries. And so they all burned but it ended up eventually releasing an enormous amount of heat to the outside surrounding areas. We also tried a viscous inhibitor. Again, can't say the brand name, but it was likewise as ineffective. And all of these were done with direct injection into the module. Basically, what we did through all these results, or through these initial results, trying the same methods that other folks had been using, is we basically confirmed the theory that propagating thermal runaway could neither be controlled nor could it be stopped. Like if it's going to start in a battery, we felt, nope, this isn't stopping. This is a train that's going to run all the way through. But while we were doing that, we were identifying ways that we might be able to intercept, ways that we might be able to stop, in some cases, the propagation of thermal runaway. And in doing so, we kind of identified what a liquid would have to, how it would have to perform, what its properties would need to be able to achieve that goal. And once we did, that's when we came back and we discovered blue. And this is the first solution on the market right now that works to, in some cases, it can stop propagating thermal runaway. And in other cases, it's designed to manage the thermal runaway heat as it goes through that process, if it is unable to stop that the propagating thermal runaway based on battery design or architecture. The way it works is you have a tank of blue that is set near the ESS in a manifold that is piped directly into these modules. When a cell begins to overheat, there are a number of ways that can be detected. That can either be onboard gas detection inside of the module itself. Depending on the battery type, it could be detection somewhere else in the room. If you have a UL-rated BMS, that could be used as part of the protective system. When that is detected, the control valve on the main tank opens and it floods the network that goes to all those modules. And again, after that, depending on the system, depending on the design, you can either have a total flood of everything in your rack, or you could have a localized flood of the module that is undergoing thermal runaway to directly target that threat at its point of origin. And that, again, it can be done a number of different ways, both with passive and active actuation techniques. So we tried that. And before we did any testing with blue, the very first thing, and this is our case study, that was that same battery that we showed in the beginning. And first thing we did was a free burn. Let's just see how bad things get. And again, we measured a lot of things on this test. And the one that shows a pretty good story is the temperature on the top of that module. So we had a stick-on thermocouple right on that upper surface just to see, how hot things got. We put the battery into thermal runaway, and with every cell that failed, it added to that temperature, and it just got hotter and hotter and hotter until the surface was absolutely cooking. We applied no agent to this. All 36 of the cells inside of that module burned. The amount of smoke that came off this test was really excessive. It actually overwhelmed our 20,000 CFM blower hood that we were using to extract fumes from that room and clean them before sending them into the atmosphere. And what's also interesting is that the temperatures that were generated were sustained for a very, very long time. Once we did this test, we let this module sit for about 24 hours before coming back to it. And even at the 24-hour mark, the surface temperatures were still in excess of 100 degrees Celsius. So if there was another module nearby or above to the side, it likely would have also been triggered to go into thermal runaway just because of the heat load that was being set off from the surface, radiated from the surface. We did this test several times, and in several of these tests, even though the battery was designed for containment, flame injection still occurred in some of those tests. So we came back and said, okay, given we know that this kind of heat is going to be generated, we designed and tailored the blue system to have delivery rates and fluid levels sufficient to handle the heat load of all 36 of these going to understand that, or to absorb that energy, and in some cases carry it away. And then we ran ahead and ran that test. And the temperature improvement was alarming to us. It was very, very quick how quickly it knocked down those temperatures. And you can see in this particular example, the high temperature never even reached 100 degrees Celsius. 9540A, calls out as a stick as a lanyard stick to say 97 degrees above ambient temperature when you start is kind of a litmus test. If you get to that temperature, say it's likely that you can cause thermal runaway in a joint or a neighboring module. You can see in this particular case, it didn't even get to that level, which is a really good thing. Obviously, we didn't have to wait 24 hours for the module to be below 100 degrees Celsius in this particular case. And once this was cooled, it never reignited. And so we thought that was pretty interesting. And so we started looking a little bit deeper and saying, okay, how did that happen? How did that work? And we started looking at things like the internal module vapor temperature. So look at the data sets for both of these tests. And in the red one, that's the free burn. And just looking at the gas temperature of what's inside, what's coming out of that vent hole, you can see very clearly as these burn, you can see the cells failing on an individual level. It'll generate a lot of heat energy. And then as that heat energy is absorbed by other parts of the battery, by the walls, by the ceiling itself, it's radiated out into the atmosphere. It cools a little bit, but every cell that fails is additive, and it just keeps going up and up and up until it reaches, in this particular case, a peak exhaust temperature of 532 degrees Celsius. Now you can imagine if that is very close to another module, that would cause significant heating if you had that jet impinging on another ESS module in that same space. And then once those gases were exhausted, it led to a plateau of about 316 degrees, which lasted at that level for several hours before eventually starting to cool. And like I said, about 24 hours later, it was still just above 100 degrees Celsius. What was interesting is going down and looking at the blue curve. That's the test that we did with blue. And you don't see as many of those sawhorse signals. And what we determined and later confirmed by taking the module apart and doing a post-mortem examination is that in this particular test, only about 6 cells failed. The initial thermal runaway event involved 2 of the cells, the ones that were on either side of the heating pad, and they went essentially simultaneously. But 6 cells were involved as opposed to 36. That led to a peak initial temperature of 114 degrees Celsius. And, in a longer sustained period, once it was full of blue, it was much lower and again continued to fall. So the vapor temperatures were drastically reduced. And the case temperatures, as we already saw, were also drastically reduced. One other point that's really important to note is, as compared to the free burn, by only allowing a certain number of cells to undergo thermal runaway, which happened essentially during the time that we allowed ourselves to fill that module, which takes a couple of minutes in this particular case. We were releasing those gases, but then we stopped. As soon as we stopped allowing cells to go into thermal runaway, we stopped generating gas. And that's really important for several reasons. One of those reasons is that if you have an active ventilation system, it would have to be a pretty high flow rate active ventilation system. But if you were using active ventilation, that in combination with blue would provide the opportunity to get things below the lower flammable limit for those exhaust gases inside of the ESS enclosure. Also, every cell that goes off generates toxic gases. Those can be very noxious. They can trigger asthma or respiratory issues for people who are nearby. And so by minimizing the level of those toxic gases as quickly as possible, drastically reduces the impact to the environment and to people that are nearby. So it's a pretty big deal. Something we've also noticed in subsequent testing is that the exhaust gases that come off from one of these batteries, even during a blue test, they exhibit a drastic reduction in particulate matter. And a lot of the particulate matter that comes off of these batteries is graphite, which is a necessary component of the manufacturing of the battery. But there's a lot of other particulate matter that come off from burning of plastics, incomplete combustion of electrolyte that puts more particulates, harmful particulates, into the air. Blue actually absorbs those. Based on the amount of plastics that are involved in these batteries, those gases that can be generated, like hydrofluoric acid, hydrogen cyanide, there's a component inside of blue that has been designed specifically to absorb and neutralize those acids as well. So you can see there's a very strong benefit to limiting the number of cells and then being able to capture and control a lot of that pollution that comes off of that. And this is all good. And then the question is whether or not, this, even though we still had a thermal runaway event, whether or not that makes a difference to a neighboring module and whether or not it can be triggered to go into thermal runaway in one of these cases. And so we're measuring heat flux above, from the module above, for this particular test. And if we look at that particular data, the results are stunning. For the free burn test, you can see in this data, we got up to a peak value of about 2.5 kilowatts per square meter. And that means that we were above the 1.3 kilowatts per square meter for about 25 minutes, which means this is an unoccupiable space. And this particular one was mounted about 6 inches above the module. We also had gauges that were measured or that were set about 3 meters away to the side and about 3 meters away directly in front of the vent. And the one that was directly in the front of the vent got so hot that it was actually destroyed during that free burn test. So being in an occupied space there is a bad thing. But with blue, the heat flux at the neighboring module was reduced down to about 0.9 at its peak, 0.9 kilowatts per square meter, which is low enough that you can be very, very close to it and not experience pain or first degree burns. And also that heat emission to a neighboring battery is low, and it stays low for the duration of its existence. You can also see in the free burn test here that heat flux load kind of leveling out right around 1 kilowatt per square meter. It stayed at about that level for about 12 hours before starting to fall with the temperature. And then once we hit that 24-hour mark, it was down around 1/4 kilowatt per square meter. But that is sustained heating of everything around it, which means when you have sustained heating, that means it's additive heat to the neighboring modules, which means it becomes very likely that something nearby would also go into thermal runaway just because this one went into thermal runaway. We see this as a huge win from the standpoint of personal safety, keeping first responders, if they have to get close to it, or if it's open already in an opened atmosphere or it's accessible, it brings it down to a level where, given the right safety protocols in place, it is possible that this module could have been extracted from the rack pretty early on in its process and then set aside and guarantee that there was no chance that it could cause continuing propagating thermal runaway inside of another pack. So if we look at this in aggregate, kind of the way it worked, the free burn versus the suppression, here's a table that kind of shows that. We're looking about over an 80% reduction in the number of cells burned, which again, that directly correlates to the gases that are generated and released. That directly correlates to the amount of toxic gases that are released. And that doesn't even include the reduction in toxic gases because of blue's ability to neutralize, or because of particulate matter being captured by this particular liquid. The suppression test was over in a fifth of the time of the free burn, which means you have time to ventilate, you have time for the atmosphere to carry some of those gases away and reduce the concentration of those gases near populated centers. There was a really dramatic decrease in the peak vapor temperature, what was being let off for that, but also what's not captured there is the duration of those. Like during the actual burn, half an hour to 6 minutes, but it's half an hour at 500 degrees Celsius versus 6 minutes at 114. It's a pretty big difference in terms of its thermal load in the atmosphere that it's going into. The settled vapor temperature, so after the thermal runaway events were over and the pack was just sitting there breathing after the fact, significant reduction, also about 80%. The heat flux was a big one. We're about a 96% reduction in heat flux of energy going to an adjoining module, which is a really, really, really big deal. And then what we didn't show in graphs was the actual temperature. So we talked about heat flux being additive to the module above or the module to the side. The longer it goes, the higher things go. The day that we did this test, it was about a 14 degrees Celsius day. Not warm, not cold. But you can see during the free burn, the module above got up to about 236 degrees surface temperature, directly 236 degrees Celsius, directly above the battery. So the module above, if it had been populated with lithium-ion battery cells, almost certainly would have gone into thermal runaway at that level. Whereas if we take that exact same system with blue, it got up to 19 degrees, so about a 7-degree rise. That's well within the normal operating temperature for one of those batteries. So unless it was experiencing a similar type of electrical failure, if that was coming from a power grid spike or a BMS system failure that caused overcharging of everything in the rack, this module that was under fire was managed to a level that it would not have caused thermal runaway in the module above. It's a very positive result in that regard. So it's one thing to talk about these, but we should look at them. In this particular video, you can see the top one, you have a module that is unprotected. The bottom one has blue protected. And you'll notice every time you see one of those chuffs of smoke, that's another one of those lithium-ion modules that is failing. The one with blue has a couple of short bursts, and the one in the very top just goes over and over and over. And so this is a loop, it's been trimmed. But the top one was continuing to go for almost 40 minutes. A couple things to notice here. One is the veracity of those plumes as they come out. You look in the bottom one, the plumes are a little bit white. The ones in the top are a much darker color. And that's because a lot of that soot that comes off the battery as it burns with blue is being absorbed. It's being controlled inside of the module. There is some runoff in this particular module because there is a drain hole in this particular setup. In the upper video, the reason the smoke is black is all that carbonaceous soot is coming out. It's constantly being blown around. And in the end of this test, every surface in this cell, even with the blower running, was coated in a pretty thick layer of black soot. And we had some of that swept up and sent off for analysis. And it was very, very laden with heavy metals and toxic elements as well. So we're very cautious in how we capture both the gases and the emissions coming off these batteries, both when we do a free burn and when we do a suppressed test, because we don't really want to put any of that into the atmosphere. What's also very interesting in this particular case with blue, the bottom video, is you do see runoff, but when we look at this particular test, we did this with about 26 gallons of blue. Most of that remains in the module. Some of it does run off as part of our safety factor. But at the end of the thermal runaway, you're looking at a few gallons of blue on the ground to clean up, which can be contained effectively using berms around your ESS, or just by having good seals at the bottom, or having the entire thing inside of have a pan below your rack. As opposed to something that we haven't talked about up till now as a strategy is just using pure water. In installations where municipal water is used, especially for direct injection, you end up using tens of thousands of gallons of water to try to control what's happening in these batteries. Unfortunately, water causes electrical short circuits. It does cause additional modules to go into thermal runaway. And then all the toxic things that are coming off this battery are no longer contained within the battery or in a very small zone around it. They are now spread throughout the area around the ESS installation, and tragically, likely into the ground and into the groundwater, which is a very, very bad thing. So this also represents an opportunity to provide that thermal runaway management solution without causing additional environmental distress or causing the necessity for a massive cleanup effort, environmental cleanup effort to protect neighboring communities and water supplies. One more note about these and the quality of those gases. The gases coming off of the lower video there with blue are extremely saturated, and we've just recently done some additional testing with another client with a much larger battery, where we were trying to ignite these particular gases. The battery that we were doing testing with was NMC chemistry as well. We know that those tend to burn, and if not flaring, they generate a high level of hydrogen and methane. And we were unable to ignite with that flammable mixture being so saturated with these vapors from blue. So that's some of the testing that we did on our own with this particular client. And what we talk about with our BHA process is that we want to test these batteries. We want to help a customer iterate on their design, iterate on a protective system to help them get their best foot forward when they go for their UL 9540A certification testing. As we all know, certification testing is very expensive. It's time consuming. It takes a long time to get onto testing schedules generally. The labs are very, very good, but they're also very busy. This is a very rapidly growing sector right now. So we helped them evolve their protective strategies and get things ready for that test. And then ultimately they went to a lab, they went to CSA. And in order to do the test, they provided 16 fully charged modules, which ended up being around 65 kilowatt hours of power. They set up their racking to use their absolute minimum spacing that they would typically see in their applications. And that included both from rack to rack and rack to the nearest surface. All of those surfaces were instrumented heavily with both thermocouples for temperature measurement and heat flux sensors in certain locations, especially out to the centers of the occupied spaces or walkways around these batteries. And they all, like we had done, also measured temperatures of the target VSS. And so that was done. And in this particular test, when they ran one of these modules, and again, these racks were fully populated, ran one module in the middle of this rack into thermal runaway using the same methods that we use at Fike. Blue was able to control that test, and the temperatures both at the target walls and the target ESS units above and to the side were never close to the UL 9540A limits. And again, looking at that that yard measure of around 97 degrees Celsius above the temperature at start. Here's what that data looked like. So this data is showing the temperature of two cells inside of one module. So they're very close together. And you can see at marker 1 there, you see the temperature rate of rise very well controlled at CSA. There's a slight endotherm followed by self-heating beginning at around 120 degrees Celsius. The cell vents at marker 2. I did see in the quote somebody that asked about gas sensing. It's at this point typically that you would generate enough gas sensing that you might be able to sense something happening outside of the battery. Depending on the battery, you may be able to sense some electrolyte vaporization before cell venting at an earlier time if you had sensing inside of the battery itself. And then at marker 3 on this data, you see the first cell begin to go into thermal runaway. And about 8 seconds later in this test at marker 4, blue was released into the system. And this particular one, we used a fully passive system. So it responded based on temperature, but there was no controller involved. And we didn't command the system to fire. We left it pressurized and it released on its own. And as blue was beginning to fill that module and start controlling that thermal runaway process, another cell immediately adjacent went into thermal runaway, and that's where you see at marker 5. Notice its temperature didn't reach as high as the core temperature on that first cell that we initiated. But both of them, once the module was filled with blue, those temperatures began to fall. Now, after that, there were a few more cells that went into thermal runaway. But by, after a little bit of time, you can see, out there at marker 6, there are no more thermal events, and it started to cool and continued to cool from there. Temperatures in other modules never got anywhere close to anything that could cause thermal runaway. So this is considered a pretty big win. The staff at CSA went back and looked at video, and while we don't instrument every single cell and every single battery, we can look at things at a higher level and say, think of it in terms of events. You see, like in that video, you see a chuff of smoke coming off. You consider that an event, and that might have been one cell. That might have been a collection of cells, but it was an event. And so they went back and they analyzed all the video. They have a lot more data than we're showing here. Fantastic laboratory. And they provided in their report for that 9548 test some of these metrics. So we would call, the start of the test, thermal runaway started at about 40 minutes, and that was with the first event of smoke being discharged from the module, which indicates that something is happening, and that's concurrent with the data with the temperatures going exponentially higher. So once that happened, there were a second through a fifth event that all occurred over roughly the next 3 minutes or so. And during that 3 minutes, that's when we had detected it with the system. Blue discharged and filled the module in that time. Took about 2 minutes. After that point, that 42:56 fifth event, and that fifth event was, I think, that was the start at 42 minutes 56 seconds. It takes about 30 seconds for it to finish out. And at 43:54, you can visibly see a little bit of excess agent pouring through the vent holes in the top of that battery. But once it was submerged, there were no more thermal events. So the whole thing was over in about 3.5 minutes. And that's really good performance when you're talking about an entire rack of thermal or of lithium ion batteries with one module experiencing thermal runaway. And they considered end of test about 10 minutes later because there were no more thermal events. Things were substantially cooling. And then they let that rack sit exactly as it was for a minimum of 24 hours. And not only did this module not reignite because the thermal runaway hazard was successfully managed. Nothing else went into thermal runaway either, because again, the heat was being handled by blue. And using something like blue, which doesn't work like water, water you would put in, boils, it goes away. Clean agent you would put in, it boils in a much, much lower temperature. And so it evaporates much, much faster, and also puts out flames, but doesn't really do anything to really cool effectively. Blue has a much higher boiling point. It does have multiple stages of actions that it goes through to manage that thermal threat, but its very high boiling point also means that it's going to stick around. It's not going to evaporate and just become gaseous and let the battery dry out and start its process all over again. Because of our approach with this particular agent, it's not an inert gas. It's not a sprinkler system. It's not an aerosol. It's not, a flood with water. It's been acknowledged at this point by certain NFPA committees, most notably NFPA 855, that this is a novel way to approach these, not as fire suppression or as thermal runaway cessation, even though, as we've just shown here, that is possible. Acknowledge that it is a thermal runaway management solution, because that's what it's doing. It's managing the heat load from a thermal runaway event. And if it can't be stopped because of its configuration, if I had 50 cells in parallel and they were all unfused, so that if one goes into thermal runaway, it shorts the rest and they're all going in, this product would still be able to manage the heat load coming from that particular hazard. And again, NFPA 855 has acknowledged that it's novel and that it can be effective. And language is going to be included soon that will start to talk about how to apply systems like this that aren't more traditional fire suppression systems. So all in all, it's a really good product. We're pretty happy with it, and we're excited to say that something can be done, something that's effective, and that has been tested on a large scale as well. Thank you for your time. With that, I'd like to open up and see if we can get into some questions here. If anybody has anything they'd like to know.
Is there anything in the list that takes your fancy, Tom?
I'm just pulling that up right now.
While you're having a look, there's, I think, Lempira from Honduras. I hope I got that right. It's got a great question regarding drilling holes in battery packs. Yes, absolutely. We try and avoid that at all costs for obvious reasons, warranty being one, dealing with the manufacturers. But in a lot of cases, we find we don't have to drill the packs. There are openings that are already made during the manufacturing process, or we step up a level and we protect that pack from setting the next pack on. So we don't look at it at a cell level. We go up a level and look at it at a module to module level. So it's an absolutely critical consideration, but something that we generally can overcome.
Exactly. Thanks, Mark. Sean, you asked about concerns about over pressurizing the casing during discharge. It totally depends on the casing. Yes, there's always a risk of over pressurization. We are pumping in as a liquid. Our liquid does not boil off very, very quickly. So it's not like with water where you'd have, or with Novec where you'd have a very almost instantaneous flash over to steam, which would cause a steam explosion. But because every casing is different and they all have different strengths, that's why we always recommend a BHA with blue. And in fact, we require it because it's always going to be bespoke for that particular battery and that particular application. We consider this to be a performance-based solution right now. There are no prescriptive design requirements in any standard. But over pressurizing is always a concern. We tend to assess the thermal limit. We know how much gas we're generating. We know how much gas we're pumping through. And we've been able to design solutions at this point that effectively manage a thermal runaway solution without causing, for example, something like a steam explosion. We don't do that. Nick, you have a great question about exhaust fans, or a statement or a question about if they need to be rated for high temperature motors. I'm not an expert in that, but I would assume so. I would also assume that they would need to be EX rated, because we know that the gases coming off of lithium battery fires have high levels of flammable gases inside of them. And so I would imagine high temperature and explosion proof would both be a necessary aspect of that. Personally, something that I'm a little more familiar with, I would recommend explosion venting as a necessary co-product that would go along with any suppression system with ESS storage, because the gas is flammable and it does generate explosive atmospheres inside of those enclosures. And when you have explosive gases and lots of opportunities for ignition sources coming from a battery undergoing thermal runaway, the risk of explosion is extremely high. So, and also the ability to spool up a fan or a blower with enough capacity to maintain an enclosure below, for example, 25% of LFL would be impractical. And so a passive and faster acting relief system is probably more warranted than using active ventilation.
It's kind of something we touched on in the last webinar, and it's something to bear in mind as well, is making sure you understand how these safety systems work together with each other. You can end up in a situation where you've got venting and certain types of fire suppression, and actually the fire suppression will work against the venting. Or you'll end up releasing the gas because of overpressurization. So making sure you have somebody looking at your safety systems that from a holistic level as to how they're all interacting with each other is kind of critical for these applications.
That's a very good point. Yeah, the fight between fire protection, inert gases or clean agents as fire protection for the ESS, and venting, they are at odds. Blue is the only one, to our knowledge, that you could use both at the same time, and they would not interfere with each other. David, you have a statement about ESS modules being fully enclosed and able to contain the fluid, and that a lot of older ones have leaks, things like that. And can we use it in those non-tight situations? Absolutely. So that's another reason why we recommend a BHA, is if you have a system that could leak or might leak during one of these events, we try to design our system to account for that leak rate. One of the benefits of blue also absorbing a lot of the byproducts that are coming off these batteries is that it tends to thicken it a little bit, especially in the lower portions of that enclosure. That actually helps to seal some of those gaps. We don't like to count on it sealing it, and so we tend to design with additional fluid to account for the likely leak paths. As we saw in the video here, we were trying to account for a likely leak path that actually didn't open in that test. And so that can absolutely be accounted for. Yeah. Would I be able to share the names of manufacturers' equipment that we have thus far passed their 9548 test using Fike Blue? That's a commercial question. I'm in engineering.
We'll have to get back to you on that one. I'm not entirely sure if we can or not. If we can, we'll give you something following the webinar. Yeah. Nick's got an interesting question. Is this applicable to other lithium chemistry other than NMC? The heat propagation problem, the initial cause is the same, no matter which type of chemistry to some degree. Yes, the gases that are produced will be different. The temperatures that thermal runaway is initiated is slightly different. But we do see, the same effects, and ultimately it is the same problem. It's a thermal management problem. We've still got to suck the heat out, and that's where blue comes in.
Mm-hmm. Yeah, it's a great question. Jonathan asking about the 100% outgassing doesn't look preventable. It's not. Battery packs should have some kind of pressure relief. In fact, a lot of prismatic cell assemblies at that level already have cell vents installed on them. Packs in general should have breather elements. That's usually not enough to provide explosion relief, not enough area. And as mentioned before, the idea that active ventilation to the level where you could prevent or stay below 25% LFL doesn't seem terribly feasible, especially given the gas generation rates that are typical in full assemblies. For example, you might do a test, a 9548 test at the cell level with a prismatic, and understand how much gas you're generating. You might even know how quickly you're generating that gas. But when that's inside of a 10 prismatic module that's a subassembly of a pack, in our experience, all 10 of those go into thermal runaway generally simultaneous, and you're not generating 30 liters like you would at the cell level. You're generating 3-4 cubic meters of flammable gases, which is definitely enough to pass inside of your enclosure, pass through that flammable limit very, very quickly. And so to have the active ventilation deal with that, you wouldn't be able to spool it up generally fast enough, and you'd have to have enormous flow rates to stay at that level. Philip or Philippe, how has the AHJ reacted to your product? Great question. We've had awesome meetings with several people out at our test facility where we've done demonstrations of this, and that has included committee members from various committees in NFPA. It's also included fire marshals, other industry experts to come out and just see it, interact with it, ask the hard questions, have show data, and watch these tests happen live. And their responses have been overwhelmingly positive, such to the point where they've come back to us and asked us for application of blue into several other areas. And while we agree that blue should be put into a lot of those applications, we're working on it. It takes time to develop a product to be able to hit all of those markets at the same time. So
Hannah's got a question on the amount of blue. Is it based upon the area within the protected space, or how many cells? Both and none. It's very much dependent on the application, the battery module, how blue flows, what kind of heat we can pull away. So we kind of need to have a look at the batteries and the modules to be able to get a gauge as to how much blue we would need. Whether we need to hold it in there or flow it through. All of these kind of questions really need a bit of an engineering assessment when we take a look at the application itself.
Absolutely true. And yes, it's the amount of free volume matters, the location of vents, as David pointed out, the leaks, if leaks are there, those all play into it, right along with the actual energy. So the quantity of cells doesn't matter as much as the total energy in kilowatt hours that are inside of that particular module. But those all kind of play along together. It's great questions, really great questions.
Awesome. Thank you, everybody. I think we're pretty much at time now. So if there are any questions we haven't got to, we will get to after we finish this webinar. But I'd like to thank everybody for joining us. And if you do have any further questions or inquiries, please feel free to reach out to us and we'll get back to you as soon as we can. Thank you very much. Take care, everyone.
Thank you, everyone, for your time. Appreciate you.